Yeah, the next speaker is Dan Thompson. He will talk about diamonds.
That's right. I didn't have time to come up with a really funny title, so there we are. I'm going to talk about three papers. One set of works which is by people in this room and people not in this room. So Joachim and Ryan aren't here, but the other authors have been here. And something new with Dimitris, PhD student that actually Carlos and I are working with separately, who might be watching on Zoom, so if he is, hi. Now, I tried to take Masahito's lead, which is to say I won't give any of the details because they're all coming in the paper that's coming out tomorrow. But to manage expectations, the paper's not coming out tomorrow anymore. And it really is the fault of the organizers for inviting such fantastic speakers, and for the speakers for doing such a fantastic job, and participants for having such in-depth evening discussions that I failed to finish the paper. So I'd like to thank you all very much for your contributions. And you'll notice the last author here is in fact you, for your forthcoming works on this topic. And that's kind of the point about this talk is I just want to introduce you to what I think is a very nice set of ideas and something that I think you could pick up and run with and probably deploy in your research life. It might be a solution looking for a problem, but there is something very elegant in what I'm going to describe. Okay, so a theme in this conference and over the past little while is that there seems to be some nice way of rethinking about integrable field theories, and integrable systems, not in fact simple, because we get to have lots of conferences about them. If they were simple, we wouldn't. But integrable systems are in fact complex. That's the idea. So in fact, what we kind of see is some trade-off between integrable data in D dimensions and holomorphic data into higher dimensions. So that's the idea. And hopefully, things up here are much more simple than things down here. So, we have some explosion of integrable sigma models at one point, and they were coming from all over the places. And, we had this sort of garden of models, but maybe we can give them a central framework. So I guess this is about seeing the universal in the everything, which is something that Carlos likes to tell me I need to do more of. So there we are. I need to be more Aristotelian. Exactly. Right. So what we saw in other talks this week is we started with some two-dimensional integrable model with some particular lax connection. So some flat connection that depends on an auxiliary parameter Z, the spectral parameter. And the poles of the flatness in Z, if you do the evolution, provide you a field equation with Bianchi identity and so on that characterize the theory. Okay, so we're very familiar with this. And the big idea that we've seen is that we shouldn't think of Z as some auxiliary object. We should think of it as a geometrical object in two higher dimensions. So instead, we're going to consider our world sheet times some sphere. And complex numbers really here, they're points on the CP1. And we're going to consider a theory up here in two higher dimensions. And the theory that got considered was some sort of Chern-Simons-like theory. Okay. Good. And the idea here is you need some auxiliary object, which is omega, which is some differential on this sphere. It's not really holomorphic because it's got poles in it, it's meromorphic. And so the locations of the poles, the zeros, their residues, etc. So all of the analytic data informs what your lower dimensional field theory is. Okay, amazing idea, brilliant. Okay, there's another class of integrable models, which I'm going to call IFT4s. And what do I mean by these? I mean, in particular, models that their equations of motion can be repackaged. It's not in a lax connection, something slightly different. They can be repackaged in a self-dual Yang-Mills connection. Okay. So I'll come back to this in a second. So there's a sense in which these are integrable. And there's also a very similar correspondence here that dates back a lot further than what we're talking about just now. It actually dates back to the late 70s, early 80s. I've lost the... Okay, so the idea is that this four-dimensional integrable model also descends from some sort of parent six-dimensional integrable model, which basically looks exactly the same as this, except I'm going to write a calligraphic A and a big omega. So I'll just rewrite it. Okay, so omega here is a 3-0 form. I've not told you what the space I'm integrating over is, so that's an interesting point. I'll have to get back to you on that. But the idea is, by specifying the details of this omega, we can construct four-dimensional integral models. So that's nice. But we can do another thing, which is we can just sort of ruthlessly truncate these theories. We can do some dimensional reduction, right? So we can impose some symmetry vectors and say, let's look at the sector where fields don't depend on those vectors. And that gives us a dimensional reduction. Maybe I want to make this arrow a little bit different in spirit. So I'll make it a wiggly arrow. Wiggly means I don't really know what I'm doing. Whereas these ones mean I really do know what I'm doing. And similarly, from 4 dimensions, you can do a wiggly arrow, dimensionally reduce, and you get this diamond of ideas. Okay, so that's the sort of setup. So I want to tell you a little bit more about this diamond, but mostly I'm going to talk about this part of it today. Okay. So history, first of all. History. Okay. So in 1975, there was the discovery of the instanton, right? Finite action solution to Euclidean Yang-Mills, right? And there was a lot of work that went on. So obviously solving Yang-Mills is really hard, right? Second order, nonlinear, horrific PDEs. But if you solve a simpler system, so if you solve this system, F equals star F, okay? Now you've got first order equations, first order differentials, so much easier. This implies that you've also solved the field equation, right, by virtue of the Bianchi identity. So you can solve this equation, let's say for SU2, and you find solutions and they're characterized by some topological charge and so on. And then there was quite a kind of period of ad hoc generalizations of this initial solution. So can we change the group? Can we include multi-centers? Can we, there were a number of pieces of work by many authors. And it was really only the seminal work of 2 groups. So the paper's published together, but they're 2 groups. And the story behind that's really interesting, and there's a nice video. So this is the famous ADHM paper. So there's one group and there's another group. And what they did, and this is really quite amazing, is they worked out a way to solve all possible equations of this system, all possible solutions of this system, using just matrix multiplication, like no solving differential equations at all. And that's just an incredible feature. So this reduced this complicated thing to just matrix mechanics, matrix commutators. Okay, so nowadays you go, oh yeah, it's just a D term, F term, brain intersection, blah, blah. But back then, it was just a beautiful piece of mathematics. And lurking underneath this beautiful piece of mathematics is in fact this arrow, okay? So how did they really do it? They converted this question into a question up here about holomorphic vector bundles, so holomorphic connections over what's called twistor space or CP3 or something like this. And of course, these colleagues knew how to classify vector bundles, right? Vector bundles over CP1 are quite easy to do. Over CP3, there's a little bit more subtlety, and there was some maths, the machinery. Lewis has promised to explain to anyone who asks him Horrocks's monad construction over coffee, so please talk to him. But there's some serious machinery that's all living up here that allowed for this amazing solution. Okay, so there's some important prehistory, but let's just sort of get a feel for why any of this might work. So, yeah.
Do you need a classification of vector bundles or classification of vector bundles with comment?
Both, in fact. So you go from vector bundles in some bigger space, some embedding space, to vector bundles with connection. So the ones that you actually classify aren't the UN things. There's something. Yeah. Yeah, you need to know how things change over certain cycles as you go across CP3. That's the idea. Yeah. Okay, so let's just put some coordinates on R4. So everything here is going to be on R4. And let's look at what this equation is. And it tells you that the holomorphic part of F must vanish. The anti-holomorphic part of F must vanish. And and the mixed part must sort of obey some constraint equation. That's the same as Kähler-form wedge F, the connoisseurs. Okay, so this is three equations that are contained in this self-duality. And so amazingly, we can form a lattice. So here's your lattice. We're going to have two differential operators. So one is going to involve the Z derivative and the W bar derivative. And the other one is going to involve the other derivatives. Something like that. Hopefully I've not made a mistake. Okay, so zeta here is a spectral parameter, the point in CP1. And modulo the actual correct equations, the commutator of this thing being 0 is if and only if self-dual Yang Mills. Okay. So there is a lax packaging of these theories. So
the covariant derivative is with respect to the gauge connection of F, right?
Yeah,
so that's why when you commute them, you get F.
Yeah, commuters give field strength.
Okay.
Yeah, so this is integrable in two senses. It's integrable in the sense you can integrate it, you can solve all the solutions. And it's also integrable in this more sort of fancy sense that there's a lax formulation. Okay. So the idea here is that we form, and I'm going to be very schematic because there's some bits here that need a bit of care. We're going to form a 6D connection. But it is going to be of type 0, 1. So it's anti-holomorphic connection. On what is roughly speaking the space of our Yang Mills times our spectral parameter. Okay, and it's got two pieces. One piece I'll call it A dot. So these E bar A dots, we won't really define them, but they're anti-holomorphic one forms with legs in R4. And then it's going to have another piece which has a leg in the CP1 direction. So that's our 6D connection. And we look at flatness of this connection. And this has two legs. it has a leg in CP1 and a leg on the R4. And that gives you one equation, which basically constrains the way that these functions depend on the spectral parameter. In fact, it constrains them to look exactly like this. And it has another piece, which is the one where we have two legs on the R4, and that spits out for us the lattice connection. Lattice is the lattice. Okay, so that's the basic idea that's going on behind all of this, is that we can go up 2 dimensions and recast everything in terms of holomorphic data. But what we're going to do, and this is all done, of course, by the seminal works of Ward, and then it was utilized all over the place. But what we're interested here is the action formulation. That's the key point. Okay, so we're interested in this case where we have omega, which shows lines. Okay, so any questions there while I do some order raising? Lovely. Okay, so I told you the upstairs space is R4 times CP1. What I didn't really explain to you carefully was how the complex structure is on this upstairs space. It isn't the direct product of complex structures on R4 and CP1. There's some twisting. So the upstairs space. Okay, so for this talk, I'm going to take a number of liberties. So I'm going to say the upstairs space is CP3, except it really isn't. There's something called projected twistor space, except it isn't quite, it's some slice of it. But if you know what any of these things are, they're all fine for you to use at the level of this talk. Okay. Right, now this presents an immediate problem. So we need this thing, right, this is a 0-1 form, this is a 0-1 form, and this is a 0-1 differential, so that's a 0-3 piece. So if we want to integrate, we need a 3-0 thing to make a top form. Right, so there's an immediate problem. There is no such omega 3-0 on CP3, just doesn't exist. Okay. So there's various things you can do. One thing you can do is add on extra fermionic coordinates. And that's what Witten did. And that has a whole beautiful story in twistor string theory. Not talking about that today. The other thing you can do is just accept that and say, let's just have some meromorphic object. So it doesn't need to have zeros, but it does need to have poles. So roughly speaking, omega will have some function of CP1 times some differential bit. And it's this function of CP1 that's going to have all the juice going on. And it's going to have at least four poles, two second order poles, second order, 2 first orders, got to add up to 4 in the denominator. And you can understand that in terms of being able to take the projective quotient, which is what you do. Okay. So that's the game. We have to specify omega, and we're going to specify 2 choices. So I'm going to draw my CP1, my sphere, and one choice we might consider is to have 2 double poles. And we'll put these double poles at particular points. So I like pi to mean the CP1. Sometimes I use theta, sometimes I use pi. I prefer to paper for that. So these will be a pole at pi equals theta. This will be a pole at pi equals 2 points. All right. And so this example was very beautifully explained in a work by Bittleston and Skinner, and it leads to a 4-dimensional IFT. And that is in fact the four-dimensional counterpart of the two-dimensional Western-Witten model. Okay. And if you complete the reduction, you can get to the two-dimensional Western-Witten model and certain deformations thereof. So that's one option. Another option is maybe you could resolve this second-order pole at the bottom, split it up into two first-order poles, alpha, alpha tilde, and beta. Okay, and that's what my collaborators and I did in our first paper, sort of knowing from the 4D Chern-Simons what the answer ought to be. And the answer is some sort of lambda type deformation. So Svetsos introduced these lambda deformations of Western-Witten models, and that's the kind of thing we get out here. So it's some lambda deformation Western-Witten 4, which descends down to some lambda deformation of Western-Witten 2. And I might try and talk a little bit about that. So I guess the next thing I want to do is explain how this actually works mechanically. What's the steps that you have to do? Yeah.
Are you restricted to four poles and
Right. So you could up this 4 if you also put in some zeros. This thing has to be defined on CP1, so it has to have the right scaling. This thing is like a section of O plus 4, so you need something that is. Yeah, not quite. It's more just making sure that you can go from C4 to CP3, which has some projective identification. And that sort of forces this on you.
Can you also get an eta deformation there? Or
So we haven't done that in principle. Yes, I think it depends on how you
do the
reality conditions and so on, but we didn't.
So, but you know that
As
you
I
get
said,
you know
as I
that you
said.
get the lambda, right? So there is a way to distinguish between lambda and eta clearly.
As I say, there's plenty of scope for you et al. To write papers on this. Yeah.
Maybe where is lambda there?
Yeah, I'll come back to it. So there's a few places it can enter. One is that you have a natural parameter here, which is the resolution distance between the two poles. That's one extra thing that you have here that you didn't have here. But it's actually more subtle where it really comes. There's also some choices about boundary conditions. So I need to explain a bit more before I get to that.
You can resolve the other two poles.
I dare say I just haven't done that. So there's another. Actually, Ryan might have done that. No, anyway, yeah, good, probably. Okay. So who's read Polchinski? Chapter 1. Okay. So if you've read Polchinski Chapter 1 as a grad student, you've got faced with this equation here, and you've gone, what on earth is that? Because he writes down something like this. I remember seeing that for the first time, being very confused, but it is true. So if you take the antiderivative of a holomorphic function with poles, it doesn't vanish. Typically, you get delta functions at poles, right? And that's what's happening here. So this omega has poles. So d bar omega is not 0. So this thing is delta and possibly derivatives thereof. Okay. So there's some, if you like, it's almost as if this Chern-Simons theory has boundaries. You could imagine cutting out the poles and imposing boundary conditions instead, right? Now there's a famous result which says if we take Chern-Simons, even plain vanilla Chern-Simons plus boundaries, and this is where like a condensed matter theorist might wake up, right? Because this is very physical. Chern-Simons is pure gauge, but when you put boundaries in, would-be gauge degrees of freedom actually become propagating, and they become propagating on the boundary. So you get edge modes. Okay. And that's really the whole game of this story, is we prescribe certain pole behavior. We realize that we're going to have to deal with the fact we've got some boundaries. Would-be gauge symmetries get broken and become propagating. and we're going to have some edge modes. There's going to be a delta function in the poles, which means we don't need to look at our 6-dimensional theory. We just have to look at it localized to the poles. So a 4-dimensional theory. And it's these edge modes that live in 4 dimensions. So that's really what's going to happen as we go from 6 to 4. Yeah.
So are you going to get a different theory for each pole?
Let me come back to that momentarily. Okay, it's a little bit subtle. No is the answer. Get coupled theories. Okay. Okay. All clear? What's the time? You've got 2 minutes left. So I probably won't talk about everything that I could here, because I think it's nicer just to explain the basics properly, or improperly, whatever. Okay. Okay, so here's the method. So it's going to seem like a bit of a weird method at first, but it really does work. So we've got our connection A, but we're not going to use this. We're going to reparameterize this connection. And the way we're going to do it is entirely daft. We're going to write it as the formal gauge transformation of another connection. Okay, and I'll call that new connection A prime. That seems really stupid, but I'll come back to why it's not stupid in a second. So G hat is really a map from 6 dimensions to the group, whereas the A's are algebra map. Okay. So why would we do this? Well, it does make one thing clear, which is if you look at the Chern-Simons part of the action and do this prescription, we're just doing a gauge transformation of Chern-Simons, right? But here's the beauty. The Chern-Simons theory is almost gauge invariant, but not quite. So it actually picks up a total derivative piece. It looks like this. Okay, so total derivative of connection wedge right form. And it also picks up a Western piece. Okay. And you know, this is the thing that means you quantize your Chern-Simons level, right? This theory. Without a boundary, you don't care about this. With a boundary, you do care about this because your theory is not gauge invariant. So you're going to have to put some boundary degrees of freedom to cancel some anomaly and flow through the bottom. That's the idea. Okay. So here's the idea. G hat at the poles are our 4D degrees of freedom. And those are our edge maps. And we're going to extract the action. Roughly speaking, we're going to integrate by parts. There's a D bar. That D bar is going to hit the omega. That omega is going to pick up some delta function. And so we're only going to depend on G hat at the poles. That's the rough idea. Okay. Good. Of course, you know, I'm a total snake oil salesman here because I've started with a connection and I've given you a new connection and a group field. So I've just like created some degrees of freedom out of thin air. So I shouldn't be allowed to do that. And of course, I'm not. This parameterization has got an entire gauge symmetry's worth of redundancies contained in it. Okay? So there's actually quite a lot of symmetry here. So there's the original gauge symmetries that A enjoys, but there's now some new gauge symmetries that encode the reparameterization choices between G and A prime, which are also like gauge symmetries. So you've got to be a bit on your toes about it. But one of the things all of these symmetries do allow us to do is gauge fixed. And this bit is actually important. You can gauge fix A prime to have no CP1 level. Okay, that's an important point. And I think that's done in various other places in the environment too. Okay, so that's the first thing. We're going to do this edge mode trick. The second thing we have to really face up to is, I've said we've got Chern-Simons with boundaries, so you should wonder if I've defined my theory. And I haven't, because I've not given you a boundary condition. Okay, so we need some boundary conditions. Okay, so if you vary the action, you're going to get some boundary conditions. Again, d bar omega, delta function on the poles. Hang on 1 second, Andrea. That looks something like this. Okay. So you're going to need some boundary conditions on your original A, not your new A, your original A, that ensure this goes to 0. Okay. And I'll just complete the story and then revert to your question. And then the really clever thing is, once we know the boundary conditions on this original A, so that's part of our choice of data upstairs, we can plug them into this to form some relationship between A prime and G. And we can then plug that relationship into here, and then that gives us our edge mode action. So, like, for example, you could just say maybe A vanishes at the poles. Right, that would be all right. So if A vanishes at the poles, and that's a 0, then you can clearly see that you can just, stick the G's on the other side of the equal sign, and you solve for A prime in terms of G. Okay, and that is the mechanics of how you get the theories out. Right, yeah, Andra.
So is this achievable always? Is the vanishing on CP1?
Yeah, that's the internal gauge symmetry. I think that's always achieved. But then if you're talking about other spaces, other hypercalar vibrations, like here, I think yes. Yeah, good. Any other questions? It looks a little bit weird because I'm working on a patch here because I'm using zetas. But if I was using homogeneous coordinates, you would be less concerned. Okay. Yeah. Yeah, well, actually, there is a sense in which putting A to 0 is, in fact, living in an isotropic subboundary. So there's various ways you can set this to 0. Yeah. One way is you could demand that these A's live in an isotropic algebra, but it's isotropic with respect to this defect algebra. It's a bit more elaborate.
How does that affect the?
No, it is exactly what I'm doing. Okay.
Okay, right.
But there are also cases where I can set this to 0, and it involves space-time mixing with algebra stuff, and that's actually what we do here. And they're a bit richer. Cool. Yeah. Yeah. Okay. So let me see if I can complete this story. I probably won't say much about gauging then, but. So what we're going to do, let's do this example first. And we're going to put boundary conditions. So I'm going to put the boundary condition that A is going to vanish here. And I'm going to put the boundary condition that A is going to vanish here. Okay. And I've got my G hat. I told you there's a lot of extra symmetries here. There's enough extra symmetries to set G hat at beta to be 1. We can do that. But we'll have to give G hat at alpha a name, and we'll give it the name G. Okay, so it's the evaluation of the 60 field. The derivatives in this case don't enter the CP1 derivatives. You can treat them. And so this thing, you do all the story that I've sort of outlined, and you find indeed that you get G inverse DG, G inverse DG. That's just a kinetic term. Plus integral of R4 times an interval. Omega is a different omega to other omegas in the game here, unfortunately. Omega alpha beta times trace G inverse DG. Okay. So omega here is some particular two form. In particular, if you take alpha and beta to be antipodal points, as I've drawn them, it's actually a Kähler form with respect to the complex structure defined by alpha, something like that. And this is the structure of a Western-Witten model, kinetic term plus Western term. And indeed, if you dimensionally reduce, basically you can set this thing to 1, or actually any number. So you get Western PCM plus Western term, including the CFT point. So that's kind of cool. Okay.
These boundary conditions, so you are choosing these ones, but how general can you?
I think that is actually an area where there's more scope for evolution, which is understanding the full scope of boundary choices. Yeah. So these are sort of the Dirichlet-like. There are Neumann-like ones, and you could distribute them across the poles. So I think there's probably some. Yeah, maybe it's already answered in 4D and let's tribute the other. Good. So in this case, this deformed case, nothing different is going to happen at this double pole. Okay, so we'll do exactly what we did here. But now we'll do something slightly different at these poles. Schematically, and this is really schematic, we're going to relate A at alpha is going to be like some number times A at alpha tilde. Okay, that's very schematic, but in fact it does solve that this thing vanishes. So I'm not solving this locally as a boundary condition. I'm letting it talk between the two poles. So this is another place where I've introduced a deformation parameter. I've got this distance, that distance, and now this number. So it's quite rich. And the fixing here, we need to know what the value of g hat is at alpha. So we'll call that g, but also the value of g hat at alpha tilde. And it can't be 1 because we've already done that trick, so we can't fix that again. So we have to deal with the fact that we have now 2 fields. That's kind of fun. And that was a bit of a surprise to us. But in fact, it's a 2-field equation. Again, its equations of motion can be packaged in some anti-self-dual connection. So it's all integral in the same sense. But now it's got g and g tilde. And the action is quite complicated. It involves kinetic terms for g, kinetic terms for g tilde, but current interactions between these sectors. And in fact, if you go down to 2 dimensions, this corresponds to a theory that was nicely studied by people in this room, a 2-field lambda model. Okay, so that was the result of the first paper. And now I'll just outline the second paper, depending on, have I got, well, I didn't start exactly on time, did I? Yeah, okay. Plus, you know, it was a big dinner last night, so no one's that hungry. Okay, any quick questions at this point?
When you say first paper, you mean the one on the type?
Yeah, the first of the 3 that I wrote up. So that's the deformations from twistor space.
You don't get a normal line.
So in 2 dimensions, there is some particular point where there's some enhanced symmetry. And then there's some enhanced gauge symmetry, only in 2 dimensions, not in 4 dimensions, that allows you to gauge to the diagonal subgroup of these things. And then you in fact do get the single parameter lambda deformation.
You in this way you describe the, let's say, the conventional lambda model, or you mentioned something with 2 groups.
Yeah, this is the one with 2 groups, different levels, the current off diagonal currents in the yeah. So it's quite a rich, elaborate model. So. All right, so gauging. We know that a lot of the interesting integrable models are not really based on group manifolds, they're based on cosets, okay? Especially if we do string theory. So we want to extend this idea to the framework of models defined on cosets. And we're going to do this by gauging. So we're going to gauge this diamond picture. And you know, initially I had no idea how on earth would you gauge a gauge theory. It seemed like a complete mystery. I didn't really understand. But there's a hint. Now, this is quite an important hint. So this is a calculation every single grad student should do. So there's a notion of the gauged Wettermino-Whitty model. Okay, and it's not as simple as just changing derivatives to covariant derivatives, because you've got a Wettermino term. Okay, so you have to work out how do you actually define some gauge completion of a Wettermino term. But that's asked and answered. And you know, you can look at the appendix of homomorphic factorization or something like that and it'll tell you what. So these are very nice. But there's a really amazing identity which tells you you can write a gauge Wettermino-Whitty model. So G is in G and B is in the algebra of some subgroup, H sub G. This is the Wettermino-Whitty model on G minus the Wettermino-Whitty model on H. Okay, so that's kind of, this is the formulation that leads you to the post-set construction in CFT. Okay. So if you're a CFT person, you use this. If you're a geometer, you use this, but they're equal. And that's a big hint because we just saw how do we get this thing up in 6 dimensions, right? It's just this Chern-Simons thing on a G. I could probably write this down in 6 dimensions as a Chern-Simons thing on H. So my obvious guess is to go S60 A minus S60 B, where B is now a 6-dimension calligraphic holomorphic connection for H and A is for G. And that sort of echoes this, right? It's not quite true, doesn't work. You get somewhere, but there are some terms missing, some total derivatives seem a bit wrong. And you sort of fiddle around and you realize in a completely unmotivated fashion that the right thing to add on here is a surface term that couples these two objects. Okay, and there are some wonderful words in our paper about this. Good 3 pages that are quite entertaining. But truthfully, it seems a bit out of the blue, but it won't. Okay. Good. Okay, so now you do everything I just told you, right? You go, well, this has an outflow, this has an outflow. We're going to do edge modes for everything. We're going to do boundary conditions on A, boundary conditions on B. And we need to impose some boundary conditions. So maybe the kind of thing we might do something like this. Might go like A minus B if poles equals 0. And if you're really smart, you notice I've written A minus B. In our paper, we did not notice we wrote A minus B because we put B on the other side of the equation. That's really important. And you can do all the process I said, and you get a lot of junk along the way. But miraculously, what you find is that your 4D theory everything recombines very beautifully to give you a gauged kinetic term plus this omega times the gauged Wettermino term. So that's almost true. It also gives you some surprising ingredients. It also includes some Lagrange multipliers for the connection on the morphic components. I can explain later where they come from. It's more subtle. So that's kind of fun, but it is a gauge theory. And you can do this Polyakov-Wigman trick and write it as the difference of four-dimensional Wessel-Witten models. That's kind of fun. You can reduce, and you can do a couple of tricks here. You can either just reduce and then constrain, or you can constrain and then reduce. And they actually give you different things downstairs. So that's kind of fun. And you can create new integrable models. Okay. So that's what we did in the second paper. I think that's important. But as I sort of hinted, the calculation was a bit messy. We had to sort of impose this thing a bit by hand. Covariance just jumped out at the end of the calculation. It wasn't baked in. And also, it wasn't clear how to extend this for this case. We sort of sat and thought and got very stuck about how to deal with other cases. So it felt like something was missing. And it is. So the last 5 minutes is what I want to say. And this is the current work with Demetrius, which resolves much of the tension of that paper. And it would have made that paper much shorter as well. So the idea is don't use A and B. That was a bad idea. Use C, which is this combination A minus B. That's why it's important to put B on the right side of the equal sign. So we use C and B. Okay. So this is a funny object. It's not a connection. It's the sum of connections or the difference of connections. Okay. So it's actually some section of an associated adjoint function. It's quite an interesting object. In particular, there's this H gauge symmetry for which B is a connection and C transforms adjointly. Okay. So the H inverse DH bits cancel off between these pieces. But then there's another symmetry, and this one's even more fun, which is the G symmetry, for which B is inert and C is not a connection because it's got A minus B. Okay, so something funny about this one, C transforms like G inverse Nabla G plus G inverse CG. When Nabla is now the covariant derivative with respect to B. So it mixes, the gauge transformation of C picks up B. Okay. And that is really useful because this G is going to be our edge mode and it's already covariantized from the outset. Manifest. Okay. And in fact, if you want to look at the closure of these symmetry transformations, you realize that G itself must transform under H. So the gauge parameters of G must transform under H. So G should go to H inverse G. And then you get a commutative diagram of gauge transformation. And this is something that if you've done background field method in QFT, that's actually in Peskin and Schroeder, you'd see this. Okay. And now, this thing I wrote down on the right-hand board, okay, so we just change variables, and it becomes this very nice expression. So it's exactly the same, but now covariantized. So we've got covariantized Chern-Simons term. And I told you we had some Lagrange multiplier terms. We've got some BF term. Okay. And then some amazing things happen here. Firstly, this H symmetry is exact. There's no outflow, right? Because this transforms adjointly, this transforms adjointly, so they cancel in the trace. This is covariant, that was the point, and then it cancels in the trace. So this is an exact symmetry, no outflow, no edge modes, so you don't need to worry about it. Everything you do will just be gauged from the outset. But this symmetry is not exact. So if you do the gauge variation of this action, it's exactly like the same as the gauge variation of Chern-Simons, but now with partials replaced with covariance and Western-Mino replaced with gauge Western-Mino. And this one does source edge modes, and that's how you're going to get this directly. And essentially the point now is, if you've done the ungauged model for your connection A, just use the same boundary conditions, same manipulations for your connection C, but put covariant things, and the job's done. So this makes the rather cumbersome analysis done there much more straightforward and amenable to generalizations. And the example, of course, will be the gauge deformed model, gauge deformed two-parameter integral model with single pole. And that's what Demetrius, if he's at home, is working hard on, and will be with you shortly. So I'll stop there.
So these are like classical manipulation, right? Suppose you put it in the path integral. There will be some fagate probably that you will need to do. Is there any subtlety there with fagate on the G or the H, or?
I think there's myriad subtleties to do these things quantum. I think that's really significant challenges. There is some
Because of that, I didn't think there were.
Right, if you do fagate if you do
gauge
fagate
fixing,
right.
integrating out.
I think the gauge fixing doesn't involve derivative, so you won't be able to propagate.
No, it's not so much that. It's that there's steps where we've gone partially on shell in this calculation, which I think need to be handled with a lot of care. Yeah, I mean, obviously, you know, my dream scenario is to take the 60 theory, do some equivariant localization or something like that, and spit out, you know, exact statements about quantum field. But I think that's hard.
I have a dump. So firstly, okay, you have just one B, right? In terms of the notation. And secondly, if you take the total action and you replace B with A, because there is an asymmetry in how you formulate it, right? You have connections with respect to B, but not A. Like, does anything change substantially, or?
Right.
Or
No, that there are
pick anything
no,
the-
there are two different Bs. There's a calligraphic B, which is 6 dimensions, and a non-calligraphic B, which is 4 dimensions.
Okay, so it's being called
I
A minus
have
B,
tried to be
comma
precise.
B. Those are two different Bs.
It's actually true both with calligraphic and non-calligraphic. All right. Okay. So it's true of 6D and 4D. Okay. Now, your second question was about, can you switch the role of A and B? No, you can't, because they're graded by the size of the group. One is smaller than the other. So one's a subgroup of the other and not vice versa.
Oh, okay, yeah, I mean, okay.
Of course, you could do a G mod G model. That's probably.
In so far, you formulated nicely and by uplifting certain things, high dimensions, structure. But I was wondering if you can foresee in the near future some quantum computation like giving this framework, like a normal dimension, beta function. Don't tell me you and I.
No, I mean, I think that's sort of the prize, right? Is can you make some nice quantum statement just using the power of holomorphicity? I mean, we know that holomorphicity is a powerful tool for quantum things. So, I mean, yeah, that's.
Some of the computations are really hard, and I was wondering if you can make them much easier, you can do much more.
I mean, that's what the dream would be, but of course, there's many challenges with it, and you know, there's other things you could also think about, which is like we've heard a bit about connecting to gravity and looking at the closed string sector as well, and deep brain realization. So there's all sorts of stuff that one might do.
With a cheeky question, is there a higher dimensional version of the lens?
Sure. I'm just waiting for your paper. Well, I mean, there might be, right? Because you might imagine you can have self-dual fields in 10 dimensions. You could imagine some 12-dimensional.
Well, in six, it's a problem, three form.
Yeah, but signature as well. Signature. The church changes what signature.
Yeah, so if we do this in 4D, do we get a gauge version of the unifying action of delta at all?
Yeah, so there is a paper that's sort of explored the 4D chance-time definition of that. I'm not surprisingly not so familiar with. So I won't comment on it. But, yeah.
My understanding is that you put a boundaries on the same kind of solution, and this the H is kind of the bulk solution, and this G is kind of the boundary edge.
Yeah. Yeah.
You put the boundary to recover the whole.
Yeah. There's many ways you can think of it. So the way I did it is one calculational method. The other way you could do it is just say, I'm going to close my eyes. I'm going to put some boundary degrees of freedom on that cancel off the outflow from this variation. And it turns out it's the same calculation.
It is concerning the standard interpretation, which is used in Sigma models on the language of Cartan forms.
Yes, quite right.
You have a group G, which has expansion G minus 1 multiplied by G could be presented in the sum of two objects. The first object is so-called omega form, and the second
is connection and Beerbein.
Connections, yes, connected
It's
with the homogeneous space. Yeah. And there is a vacuum, which is described by the subgroup H. Yeah. And the field which is connected with the subgroup H is a gauge field. This form is a gauge form.
Yes.
So in standard, how to say, Lie algebra, which has subgroup H, you have automatically covariant derivatives with respect of subgroup of vacuum H.
Yes.
So you can construct the covariant derivatives of the form connected with, how to say, Cochet.
That's what this is.
That's right.
That's what this is. That is this.
Exactly this.
This is this. Yes.
And
I just didn't use those words.
From this point of view, there is, how to say, language of the standard Sigma model transformed in the language of Cartan.
I did totally agree. So this thing you can view as some horizontal vertical splitting, and that's where this all happens. Yes, totally right. And in fact, if you do Schoen-Simon's gravity, you can do this stuff, and you know you write A as E plus W and A minus E minus W. It's all the same stuff, actually. It is this.
Yes. And from this point of view, if we have omega form, which are connected with generators of the Cochet, we know that omega forms transform linear under transformation of the group. So yes, that's right. So we can reproduce in the standard language any Lagrangians which could be invariant under subgroup H and use any degrees of the omega forms with a gauge field. So we can translate the standard language of Cartan for Chern-Simon theory.
Yes. Yes, yes, yes.
Yes, and what is the new in the language, which is classical language?
No,
In comparison with the language which is presented here?
No, I mean, sorry, let me be very, very clear. Like, we did a messy calculation,
Mhm.
because we weren't using the smart variables, and those are the smart variables. I mean, that's true. Yes. Yes. But this is all in the context of 6D theory. It's different things.
Mhm.
Now, I'm not claiming to have invented Cartan geometry. I mean,
Yes, but at the first part of your report, you used the Penrose language, where your six-dimensional space-time is a space of spinors.
yeah.
And, you make sure between these two approach.
Yeah, so I am in the
This
six-dimensional
Cartan
space.
approach and the Penrose approach, which uses complex six-dimensional space. Like
Yeah.
it's, how to say, a standard picture to rewrite theory in terms of x derivatives and in terms of spinorial derivatives. Right.
Yeah. I was very clear that the 6D picture has its origins in 1978. I'm very clear about that. I'm not saying anything other than
Mm, yes, thank you. I understood. Yeah.
Okay, let's think done again.